Hello everyone, thank you for joining in. So today we'll be discussing about the previous year questions on code generation and code optimization. This is a topic of compiler design. So in the same topic we had a discussion in our yesterday, like our previous session. So today it is just the extended version of the previous session. Okay. So here we will be discussing about more previous year questions on the same topic. So before continuing my session, please comment and let me know whether my audio video is working properly and you are able to see or listen to me. Please put a comment in the comment section so that I can understand that my audio video is working properly, and only after that I can start the session. So you can put a comment so that I can understand. Okay, so it looks good. Now let's start the session. Okay, so this is our first question, and this is a question from GATE 2014. Okay, it is a question from GATE 2014 set 2. So question is saying what? Which of the following is not performed during compilation? Okay, during compilation, which of the following is not performed? So we know that inline expansion is performed during the compilation. Okay, inline expansion is kind of performed in the lexical analysis phase. Okay, it kind of means like the token stream generation. Okay, after that the symbol table management, it is also performed in the our during compilation. Okay, it is also performed in during compilation. Type checking is a basic part of a compilation, right? It is done in the semantic analysis phase. Now which is left? The left is the dynamic memory allocation. So whatever is dynamic, okay, like this dynamic memory allocation or anything related to dynamic, these all are actually basically related to runtime. Okay, this happens in runtime. So this dynamic memory allocation and all this happens in runtime, and this is not related to the compilation. Okay, means after compilation of the code, while in runtime. So compilation, after compilation of the code, the next thing is that runtime. Okay, so in runtime basically this dynamic memory allocation performs. Okay, not in compilation stage. So the first question, this is the answer will be option A. Okay. So going forward to the next question, it is also a GATE 2014 set 2 question, and the question says what? So for a C program accessing array, okay, so this is a array, X is the array, and there are three other indexes, okay, three other indexes, that is xi, xj and k. So it is a 3D array, three-dimensional array. So the following intermediate code is generated by a compiler. So this is the intermediate code. Assume that the size of an integer is 32-bit. Okay, so size of the integer is 32-bit and the size of the character is 8-bit. Okay, now we need to find which of the following statement is true about the source code of the C program. Okay, which is the true about the source code. So for this question, the given intermediate code, okay, so if you see the given intermediate code, it is starting from T5. So T5 is equal to basically X and it is T4. Okay, now T4 is equal to, you can see from here, so T4 is equal to what? It is T3 plus T2. Fine, T4 is equal to T3 plus T2. Now T3 is equal to T1 plus T0. Okay, so it will look like T3 is equal to T1 plus T0 and T2 is already there. Okay, T2 is there. Now for this all T with the first option itself. So first option, it is an integer, right? Now if you see this, it is what? X 32 32 8. Okay, this is the index overall. So for this array declaration, okay, so this is the array declaration. Suppose you want to search for the element, this one. Okay, so if you want to search for the element xi, j and k. Okay, so if you, so this is the whole array declaration, and you want to search for the element this one. Okay, so how many addresses or how many elements you need to cross? Okay, how many elements you need to cross? You need to cross 32 into I. Okay, firstly I into 32 into 8, because here up to I index we need to cross whole j and k. J is 32 and k is 8. Okay, so 32 into I into 8 plus j into only 8. Okay, j into only 8 because for every j we need to cross the whole k. Okay, and the k itself. Okay, so we need to cross this much element and it is an integer. So integer means, what is the integer? So the size of the integer is 32 bit. Okay, so 32 bit means 4 byte. Okay, because 1 byte is equal to 8 bit, right? 1 byte is equal to 8 bit. So 32 bit is equal to 4 bytes. Okay, so this much byte we need to cross. Now if you multiply all them, so it will be 32 multiplied by 8 multiplied by 4, it will be 1024. Okay, I plus 8 into 4, it means 32j plus 4k. Okay, so basically this representation it is matching with our intermediate code. Okay, so this option A is matching with our intermediate code. You can check for all other options, they will not basically match. Okay, the other options won't match, only the option A. If you expand the option A like this, it will match with our intermediate code, right? I hope that it is understandable. If you have any question, please let me know in the comment section. Okay, otherwise I am moving forward. So this is a new type of question which you can face in GATE. Actually in GATE exam you can always face some new type of question, but the concept will be easier and maybe, I mean, the question will be on same concept which is already asked in the previous year questions. Okay, so prepare the concept, but the questions will be a little bit, I mean, tricky questions you can face. Okay, so you have to be ready and you have to be like what to say, you, I mean, you should be prepared for this type of situations. Okay, so that's all. So I'm going forward to the next question. It is a GATE 2014 set 1 question, you can see. So GATE 2014 set 1 question. So it is saying that which of the following is false. So firstly, starting with the first option, it is a basic block is a sequence of instructions where control enters the sequence at the beginning and exits at the end. Okay, so it is true that a basic block, I already told that in control flow graph. Okay, this is not context free grammar, this is control flow graph. Okay, so control flow graph will look like this, that is some starting, then there will be some intermediate building blocks will be there, and it will be exiting at the exit state. Okay, so these blocks, these are called the basic blocks, and it is what the basic blocks are. Simple, it is the sequence of instructions where control enters at the sequence, and I mean at the beginning, and exits at the end. Okay, control exits at the end. So the first option, it is basically true. Okay, now checking for the second option, available expression analysis can be used for common sub expression elimination. So this is true. Available expression analysis, it means that suppose we already covered this expression. Okay, suppose we already like performed the addition operation and we place the resultant to the variable a. Okay, so this is already covered. Now suppose in another expression the same situation is coming. Okay, suppose the same situation is coming, so we'll just replace the available expression. This expression is already available to us. Okay, so we'll just replace this operation with our already done operation, that is a. Okay, we'll just replace it. So available expression analysis can be used for common sub expression elimination. Okay, so for common sub expression elimination, we will replace with the available expression. So this option, the option 2 is also true. Now checking for the option 3, it is what? The live variable analysis can be used for dead code elimination. Okay, live variable analysis can be used for dead code elimination. It is also true. Okay, like in live variable analysis, we can analyze that. In live variable analysis, basically we can analyze that, I mean, here we can tell that which variables are live at which building blocks. Okay, suppose we are saying that the variable a is live at block 1 and maybe block 2. Okay, so variable b is only available at only live at block b2. So like this way we can tell that these variables are live in this block. So accordingly, if some variable is not live after some block, okay, if some variable is not live after some block, we can remove the dead codes. Okay, I mean, if the variable is not used after that, then we can obviously remove the dead codes. Okay, so this option is also going to be true. Okay, so what is the last option? Let's check it. It is x equal to 4 into 5. We are converting it to x equal to 20. So they are telling that it is an example of common sub expression elimination. So this option is wrong, right? Because here is nothing like common sub expression elimination. This is what? This is, we are folding the constants. Okay, this is a constant folding. Okay, this is not like a common sub expression elimination. I have given the example of common sub expression elimination here, right? So this is not the common sub expression elimination. So as I was telling that this is the example of constant folding, right? Not of common sub expression elimination. So I already given you the example of common sub expression elimination. So this is not that. Okay, so it is constant folding. So the option B, at the option D is only the false option. Okay, so and they are also asking for which of the following is false. So obviously the option D here for this question, option D will be the false option. Okay. If you find any doubt, you can put it in the comment section. Always will be available to you. Okay. Now I don't see any comments. Okay. So if you find till now, if you find any issue, you can obviously put it in the comment section. Now fine, we are moving forward. The next question, it is of GATE 2013. So here, so as I was telling that this question was arrived in GATE 2013. Okay. So firstly we need to read it. So it is telling that the following code segment is executed on a processor which allows only register operands in its instruction. Each instruction can have at most 2 source operand and 1 destination operand. Okay, at most 2 source operand and 1 destination operand. Assume that all variables are dead after this code segment. Okay, after this code segment, all variables are dead. Now they are telling that suppose the instruction set architecture of a processor has only 2 registers, the only allowed compiler optimization is code motion, okay, which moves the statement from one place to another while preserving correctness. So what is the minimum number of spills to memory in the compile code? So firstly, if we arrange the code segment, according to the usage, then it will be something like, firstly C, this C equal to A plus B, this is the first statement. Okay, this is the first statement, and next we can see this D and D. This D and D is basically used in the else part. Okay, this D and D is basically used in the else part. So we can directly write it to the else section. Now we can write this X. Okay, because here in the condition the X will be used, so we need to compute the X after this C. Okay, after computation of 6 we can compute the X. Now we have to use the if statement. If is telling that this one. Okay, so here y is independent, so I will just write y like this, and in the else statement you see that this D and D, okay, so this D and D computation firstly needs to be completed, and then after that we can use this D and D. So D equal to what was there, C multiplied by A, and E is equal to C plus A. Now we can use the D equal to D multiplied by D, as well as E equal to E multiplied by E. Okay, so we are just putting these two statements into the else part. Okay, these two statements into the else part. Now what we need to check, that where there would be, what is the minimum number of spills to memory in the compiled code. Okay, spills to memory. So basically spills to memory means how many memory accesses we need, or you can say how many variables we need to store into the memory. Okay, how many variables we need to store into the memory in the code execution. Okay, so firstly the main thing is that we have only 2 registers. Okay, we have only 2 registers, R1 and R2. So here you can see that, see, using these two registers, this compilation, I mean this process can happen. Okay, so this is, I mean this won't be a problem. Okay, the next thing is that here we need the memory spill. Okay, because we need to store this C star C, the result we need to store in the memory, because otherwise we need some extra register. Okay, basically we need to find that how many registers we need, and now we have only two registers. So suppose for, I mean minimum number of registers we need n registers. Okay, so how many registers are available? So two registers are available, so n minus 2. Okay, this much memory spill we need. Okay, this is the minimum number of memory spill we basically need. Okay, now let's see. So here what is happening here, basically here will be one memo, I mean we need to store this resultant as well as we need to store this resultant d equal to c cross a. Okay, this these two we need to store, but in a basic block, suppose memory, in a memory we have been defined only one section. So firstly we are allocating the resultant of 1 here, and next we are removing this one because that is already used in here. So we are removing this one and we are placing the value what is coming from the equation 2. Okay, we can place the value what is coming from the equation 2. Okay, so basically if you say this, so how many memory cells we are needing in total? So we need only one memory cell. Okay, because in using one memory cell we can execute the code because we already have two registers. Okay, we have two registers and one memory cell. So in total basically we need three spaces. Okay, we need three spaces to be allocated. So number of memory spills to the memory in the compiled code is 1. Basically, so it means that after using these two registers, okay, after using these two registers, we need one more memory. Okay, we need one more memory to execute the code. Okay, so I hope that this is clear. If you still have any doubt, you can just replace the whole code using registers. Okay, and you can see that how many minimum number of registers you need. You can firstly you can I mean take the 3 address code. Okay, you can firstly take the 3 address code, and then basically you can 3 address code to the optimized 3 address code. Okay, optimized 3 address code means you need to make sure that the number of registers is minimum. Okay, so when you will get the minimum number of registers, then suppose as I already told that you are getting 3 registers, so minus how many registers you have? You have 2 registers, so 1. So 1 memory spill you need to access. Okay, 1 memory space you need to access. So that is the main purpose of this question. Now going forward to the next question, it is a linked question basically. So it is also in GATE 2013. So it is telling that they consider the above data as previous question. So I mean the data is given for only one question, and that data is used in two or three total questions. Okay. So the same data as previous question, what is the minimum number of registers needed in the instruction set architecture of the processor to compile this code segment without any spill to memory? Do not apply any optimization other than optimizing register allocation. So basically in the previous question we had optimized the code, right? We had changed these two statements. Okay, we had like moved these two statements into the else section. Okay, because it is an optimized code, because if anyhow we are going to the first statement, okay, if right, then we are going to the first statement, then the whole section will not be executed, right? So we just move these two statements or these two instruction into the else part. So anyhow we have, I mean we had optimized the code. Okay, now that won't be the same case for this question, because it is telling that do not apply any optimization other than optimizing register allocation. So we can't apply any optimization technique. Okay, so basically let's take the code itself. Okay, let's take the code itself for our ease of access. I mean, so let it be. So if you see the code, okay, let me write the code again. So the code is there. It is C equal to Okay, let me search the code. It is C equal to C equal to A plus B, then D equal to C star A, then E equal to C plus A, then X equal to C multiplied by C. This is the original code, right? Then if X is greater than A, then if statement is executed, Y multiplied Y equal to A into A. Then else statement is also there, else is under some braces, so it is D equal to D multiplied by D and E equal to E multiplied by E. Okay, we have this much and it is closing the else statement. So this was our main code. Okay, now we need to like write this code according to the registers. Okay, so firstly we can write like register 1 is equal to register 0 plus register 1. Okay, so this was in register 0, suppose this is in register 1 and we are putting the whole resultant into register 1 itself. Okay, now here we can find that D, so D is equal to, so D is some another variable. Okay, so we can write it like this, register 2. Okay, we are using register 2 and see this C value is stored here. Okay, this C value is stored in register 1, so we can write register 1 multiplied by A. Okay, so A is stored in register 0, so R1 multiplied by register 0, fine. Then it is E. Okay, so E we can write in R3. Let's take R3, and in R3 basically again C and A. Okay, so C is in R1, C is in R1, E is in R0. Okay, so we are taking R3. Now we need to take, suppose this X. So X is telling that C multiplied by C. Okay, X is telling C multiplied by C, and in the next code section we cannot find any operation of C. Okay, so we can do like this, that we are replacing the value whatever is in R1. Okay, basically I want to tell that in R1 we have C. Okay, in R1 we have C. So now as there is no other operation in the next code of C, hence we are just replacing the value of C with C multiplied by C. Okay, it means with C cross C. So in the set of registers it will look like this, R1 multiplied by R1, and the value will be stored in R1 itself. Okay, now there is the if condition. So if condition is basically X greater than A. So here our X is stored, in R1. Okay, so this is X basically, and A is stored in R0. So R1, if R, then it will be like y to A into A. Okay, y equal to A into A. So we are not using this R0 register. Okay, we are not using this R0, so we can perform like this, that R0 is equal to R0 multiplied by R0. Okay, I hope that you are understanding that. See, this variable R0 is not used. Okay, I mean this variable A that is in the register R0 is not used in the next code. Okay, in the next part of code the variable R0 is not used, so we are just replacing the value what is in the R0. Okay, now we can move forward to the else statement. So else statement is telling that D equal to D cross D. Okay, now we see that D is in which one? D is in R2. Okay, so we can write like this, R2 is equal to R2, and same situation for R3 also. Same situation for R3 also, it is E, right? Okay, so R3 we can write like this, R3 multiplied by R3. Okay, so overall, if we are not optimizing the code itself, but we are anyhow we are optimizing the register allocation. It means we are trying that the number of register that is used, that should be minimum. Okay, number of register that should be minimum, we are trying that. So how many registers we are using? We are using R0, R1, R2 as well as R3. Okay, so total how many registers? 4 registers we are using, that we have used in the registered. I mean we have applied, see, we are searching for the minimum number of registers that could be optimized, but we cannot optimize, we cannot apply any optimization other than optimizing the register allocation. So we have only applied the register allocation. Okay, I hope that this question is also clear to you. If you are facing any issue, you can put it in the comment section anytime. Okay, so let me move forward. So this is a question from GATE 2011. Okay, GATE 2011. Question is what? Consider the two binary operators. One is the up arrow and another is the down arrow. With the precedence of operator, down arrow is being lower than that of up arrow. Okay, so up arrow is of higher precedence than of down arrow. Okay, now operator up arrow is right associative while operator down arrow is left associative. Okay, so up arrow is right associative while operator left arrow is down associative. So which of the following represents the parse tree for the expression? Okay, it means that operator up arrow is basically it is right associative. It means the right side will work first. Okay, and down arrow it is basically left associative. It means the left side down arrow will work first. So firstly, this is the expression they are telling, right? So this is the expression. So if you see the expression, firstly, I mean between this up arrow and down arrow, which is having the higher precedence, obviously the up arrow, right? So here this 3 4 3, okay, this part will execute first. Okay, this part will execute first. So in these three parts, we know that up arrow is right associative. Okay, up arrow is right associative. So this part will firstly execute. Okay, so whatever will first execute, we will write it in the bottom. Okay, so first start with this 4, then the up arrow. Okay, 4 up arrow 3. So this will execute first. Okay, so whatever the result is coming, that should be executed, I mean that should be processed with the next up arrow. Okay, whatever this is coming, it should be processed with the next up arrow, and 3 is the operand here. Okay, 3 is the operand. Now whatever the result is coming, now we can see that 2 down arrows are there. Okay, 2 down arrows are there, and down arrow we know that it is left associative. Left associative means the left side section, the left side part will work first. Okay, the left side part. So the left side part, here is the down arrow, you can see. So left side part, this will work first and the operand is 7, and after that whatever the whole result, till this part, okay, till this part it will be processed with down arrow 2. Okay, so it will be processed with down arrow 2. So this is going to be our parse tree. Now let's check which option is matching. I believe that the option B. Okay, let me change the color of the pen. So I believe that the option B is correct option. Let me check it again. Down, up, 7 3 4 3. Okay, so option B is basically matching with this question. So option B is going to be the correct option, right? This is a very simple question that can be asked in the parse tree. So if you find any issue in this type of questions, you can obviously let me know in the comment section. Okay, I hope that this is a very easy question, only dependent on the, I mean you need to have the knowledge about this precedence and associativity. Okay, what is called the precedence or what is called the associativity, you need to have the knowledge, and with the basic knowledge of those things you can solve this type of questions. Okay, so these are easier standard question. Now going forward to the next question, it is a GATE 2010 question. So this question, it is also a code generation and optimization technique question, and it is of GATE 2010. Okay, so this question was arrived in GATE 2010, and it is telling that which languages necessarily need heap allocation in the runtime environment. Okay, so in runtime environment means basically we need the dynamic allocation. Okay, so we need dynamic allocation. So in runtime environment, we need the dynamic allocation. So it is telling that those that suppose recursion. Okay, so for recursion, we basically need the stack allocation. Okay, stack allocation is basically needed for recursion, not the heap allocation. Now those that use the dynamic scoping. Okay, scoping means we are changing the scope of the variable, that can be global or local variable. Okay, so that is not related to the heap allocation. Next is that those that allow dynamic data structure. Okay, so this option may be the correct option. Let's check the fourth option. Those that use globe, right? So this global variable and all this will be like already the memory will be given to the global variables in the compile time itself. Okay, so in the compile time itself, the global time variable will be given, the space to the global time variable will be given. So runtime environment means dynamic allocations. Okay, so we need to dynamically allocate memory. We need to dynamically allocate memory, and that comes basically from heap. Okay, so suppose if we are creating a variable a, okay, suppose we are creating a variable a in our code, and that we are creating dynamically. Okay, so dynamically we are creating. So dynamically creating means it is taking the space. It is taking the memory space from somewhere. Okay, it is taking the memory space from somewhere and it is giving it. So what is that somewhere? What is that somewhere? Somewhere is the heap storage. Okay, somewhere it is taking, if we create any dynamically, if we create any space to some memory, I mean to some variable or to some array. Okay, then basically we are taking the space from the heap allocation and we are putting it to the variable or the array itself. So only the option C will be the correct option, because it is telling that those that allow dynamic data structure, and dynamic data structure means basically creating the I mean creating the memory and or creating the variable dynamically, okay, in the runtime. So option C will be the correct option for this question. Now moving forward to the next question, that is a GATE 2008 question. Okay, and it is telling that some code optimizations are carried out on the intermediate code. Some code optimization and are carried out to the intermediate code because they enhance the probability of the compiler to other target processor. Intermediate, because they enhance the portability of the compiler to other target processor. That is wrong. It does not enhance the portability of the compiler. Okay, now checking the option C, it is saying that the information from data flow analysis cannot otherwise be used for optimization. It is also wrong. It is not dependent on this. The information from the front end cannot otherwise be used for the optimization. That is also wrong. Okay, so I mean we can use the front end information for the optimization in the machine itself. Okay, we don't need to optimize in the intermediate code. But why we do the intermediate code optimization? Because the option B is going to be the correct option, because the program analysis is more accurate on intermediate code than on machine code. Okay, so basically in the intermediate code or in the 3 address code, we can understand about the program in more accurately. Okay, we can have the better knowledge on the program in the intermediate code itself than the machine code. Okay, in machine code it will be somehow difficult to like cope up with the flow of the program. Okay, so that is why the second option is going to be the correct option for the question of GATE 28. Okay, 2008, the option B is going to be the correct option. Now moving forward, this is our last question of today. Okay, last question of today, and this is of GATE 2006, right? So the question is telling what? Consider the following C code statement. Okay, C code segment is given. So we can see a loop is there. Okay, here is some error is, I think the error is there. Maybe it's for, I mean, I took it wrong. So anyway, this another loop is there, then it is checking whether it is even or not, the variable I is even or not, and it is just increasing some variable. Fine. So which one of the following is false? Which one of the following is false? Firstly, the code contain loop invariant computation. The code is containing loop invariant computation. Loop invariant computation means some computation which is not dependent on the loop. Okay, so some computation which is not dependent on the loop. So here we can see this if statement. This if statement, it is basically dependent on the outer loop. This if statement, it is dependent on the outer loop but not dependent in the inner loop. Okay, so we can move this if statement to the outer part. Okay, I mean we can move it back from the inner loop. So the loop, so the code is containing loop invariant computation. That is true. Okay, it is not false statement. The next is what? There is a scope of common sub expression elimination. So here we are finding some common sub expression. You can see 4 multiplied by j and 4 multiplied by j, we can just remove them. Okay, we can remove one operation and we can place the value that is taken from here. Okay, so there is a scope of common sub-expression elimination, it is also true. Now third is that there is a scope of strength reduction in the scope. So strength reduction means whatever the cost for this multiplication operation, suppose this 4 multiplied by j. Okay, so whatever cost of this multiplication operation is taking, the less I mean, we can give less cost. Okay, so we can just do a 2 left shift. Okay, we can just do a 2 left shift of this variable j, and it will be actually same like this. Okay, whatever the resultant this will give, the same resultant will be given by this operation also. So it is what it is reducing the strength. Okay, because the left shift operation is less costly than this multiplication operation. Okay, so there is a scope of strength reduction in this code, this is also true. Okay, the third option is also going to be true. Now checking the fourth option, there is a scope of date code elimination. Okay, date code elimination is not there. Okay, I mean remove any code. Okay, all the lines, all the codes are necessary here, we cannot remove anything, there is no constant folding and all. So there is a scope of date code elimination, this option is basically false. Okay, so there is no date code that we can remove. So the only option they are asking for, the which is the false option, so the only option that is false, that is the option D. Okay, so option D is going to be our option that we will choose. Fine, I hope that you don't have any issue in this question. If you find any issue, you can always put it in the comment section. So thank you for joining in. Today we have solved around 9 to 10 questions on compiler design previous year question, and we also have, if you see our playlist in Geeks for Geeks Gate Computer Science channel, so here we will have the whole compiler design course. Okay, firstly we started with the content, we just teach the contents, then we went forward to the previous year questions, and almost all the previous year questions are solved in the Geeks for Geeks Gate Computer Science channel itself. Okay, so not only the compiler design, all the other subjects that you will find in the Gate Computer Science subject, all the other subjects, network, you say digital logic, maybe uh, engineering mathematics, discrete mathematics, everything is there in playlist wise in the Geeks for Geeks Gate Computer Science channel. So if you are preparing for Gate 2022, maybe Gate 2023, so keep looking at this YouTube channel, and also visit the Geeks for Geeks, geeksforgeeks.org website. There you will find the test series launched for the Gate 2022, as well as you will find the more premium courses. Okay, the more premium courses, different subjects, like already the theory of computation is launched, the